M. Frégier was a French mathematician who lived in the first half of the 1800s, and he discovered the following phenomenon. If you take an ellipse and you choose a point M on its boundary, and so this black arrow represents the normal to the ellipse at M, so if I move M, the normal is going to move. But consider the following triad, formed by the actual normal and two symmetrically rotated copies of the normal. And in this case, they're rotated by 45 degrees clockwise and 45 degrees counterclockwise. Okay, so as I reposition M, I'm going to maintain that 90-degree angle between the blue arrows and go here to the second quadrant, so forth and so on. Okay, all right, so here's what Frégier discovered and proved. Let's extend those blue arrows until they intersect the ellipse at these two blue points. And of course, if I move this whole construction, I'm going to get this kind of a situation here. Okay, and go here to the third quadrant as well. Let's stay in the first quadrant without loss of generality. Now, what Frégier looked at was the envelope of these chords that are defined by these two intersection points. As I do the following thing, let's turn the construction off and consider now rotating this pair of blue arrows with a 90-degree angle between them. I'm going to rotate them by some angle that I'm going to choose. Okay, so I can rotate this pair rigidly about M by some angle I'm going to choose. Okay, very well. Now, when I'm in the center position, I can draw that chord, but I can also watch this chord as I rotate the pair while maintaining the 90 degrees over here, right? So this is a family of 90-degree arrows that I'm rotating. So there's a right angle between the two blue arrows there. What Frégier discovered was that all these pink chords pass through one common point. Let's draw that common point. It's called F. So there's a point that sits on the line along the original normal, okay, that remains invariant as we rotate that 90-degree blue pair. And this is remarkable, per se. Okay? Now, of course, if I move M to another position on the ellipse, my Frégier point F is going to move somewhere else, and it's also going to remain invariant with respect to the motion of that 90-degree pair up there. Okay? So, given an ellipse with axes, semi-axes, little a, little b, and a point on its boundary M, you have an automatic and unique association with the Frégier point with respect to M. Okay, so a first question we might want to ask is, as I move M, what's the locus of F? Let's draw that. I believe this is it. Okay, so as I move M, let's move M around, what's the locus of that uniquely associated Frégier point? So I can put M anywhere. My Frégier point will be there. Of course, I can move my chord family, spawned off by this 90-degree dual of blue arrows. My Frégier point doesn't change. So given an M, I have a Frégier point. If I move M, I get a locus of Frégier points. And this locus just so happens to be an ellipse, which is homothetic to the original one, axis aligned, concentric and homothetic to the original one. You can see here that the axes of this ellipse have a ratio that is equal to the A over B of the outer ellipse. In this case is 1.5. So if I change my aspect ratio, I just move the entire picture, now I have an outer ellipse that has an aspect ratio of 1.81, and lo and behold, the locus of my Frégier point over all M is an ellipse, concentric, axis aligned with the same aspect ratio. So that's a pretty neat phenomenon right there. I believe this phenomenon is understood and it has been documented in publications. Now here's a new thing, and we think is a new thing. What are we talking about? let's go ahead now and turn everything off. Let's turn the construction off. And I'm going to go ahead and now reset that family of, sort of the 90-degree pair of blue arrows. I'm going to reset it to be symmetric about the normal at M, right? And I can put M anywhere. Okay. Now, I want to consider the following. I don't want these arrows to be apart from each other by 90 degrees, the blue arrows. I want them to be apart from each other by some other value. So we're at 90 degrees. Let's go to 89 degrees. Okay, so I'm here at 90 degrees. I'm going to go down to 89 degrees now. So it's a small change. Let's draw our construction again. Here we are. Now the question now is, I've deviated from the Frégier 90-degree construction. What's going to happen to the envelope of these lines? Are they still going to be a point? Let's draw them. Okay, so let's go back to 90 degrees. It's a point. It's called the Frégier point along the normal. If I deviate from that by 1 degree, all of a sudden I have something here. Let's go to 88 degrees and 87 and 86 and 85 and 84 and 83. So let's go to 80 degrees. What is this? This is an ellipse. This is showing the following, that this family of chords, as I vary that pair of blue arrows, which are 80 degrees apart from each other, now they're sweeping a family of chords, the pink chords, whose envelope is an ellipse. It's not axis aligned, nor does it have the same aspect ratio as the outer ellipse. So you can see that here. Numerically, I have the two axes being shown here. So the outer one has A equals 1.81 in this case, and let's say B equals to 1. That's what we set it internally. And then this envelope here has 0.2347 and 0.1429. It's a small ellipse, and the aspect ratio is clearly different from the outer one. So it's 1.6, and this thing is not axis aligned. But I want you guys to see, as I now go back to the 90-degree position, so I'm at 80, let's go back to 90, 81, 82. So the locus is shrinking until it becomes what Frégier discovered, which was when you're exactly at 90 degrees, my locus is a point. But if I deviate a little bit from 90 degrees, what I'm getting now is this interesting phenomenon whereby my locus is an actual ellipse. So let's go to, say, 70 degrees. Now it's 70 degrees across from these two blue arrows. If I sweep that range, the whole range, or whereby those two blue arrows are being rotated rigidly while preserving the 70-degree angle between them, I'm going to sweep a conic or an elliptic envelope, which is this elliptic envelope with center at C. So now we can ask a question. Over all M, what's happening to this locus? As the locus is uniquely identified to M, right? If you're given an M, you can just rotate this blue pair here and sweep an envelope, and you're going to get this locus. So if you think of this object, this ellipse, as an object associated with M, what happens to it as I move M along? Particularly, what's going to happen to C? So let's move M a little bit. I'm going to move M. Okay, and I can watch what's happening to that envelope dynamically. Now here's the first beautiful remark. Though these pink ellipses do not have invariant semi-axes, its area is invariant. So the area of this family of ellipses, shown up here, is invariant. I'm going to animate that by moving M along the ellipse slowly, so we can all watch this reported area of the Frégier envelope locus, which is invariant. Therefore, the ratio of the outer ellipse by the Frégier locus is also invariant. Now notice that the semi-axes A sub Frégier and B sub Frégier of this locus are varying, right? And so is its aspect ratio. However, the product of those semi-axes, meaning something that is proportional to this area, is invariant. So this is our first finding. We're not sure if this thing is known, but it looks like it's a obscure enough investigation that it might not be known. Okay, the second question that we can answer with the simulation is, what is the locus of the center of the envelope locus, right? So I have this point C here. Here's my instantaneous envelope, right? So if I move my chords, I'm going to be sweeping that envelope, but that envelope is fixed and it has a center that is associated with C, is associated with M, right? So the center is associated with M. What's the locus of this envelope? Let's draw the locus of this envelope, of the center of this envelope. And it's also an ellipse. Now what's beautiful about this ellipse is that it's invariably axis aligned with the outer one, and it is homothetic with the outer one. So it's concentric, axis aligned, and it turns out to be homothetic. How do I know this? I'm actually reporting the ratio of semi-axis here of the center ellipse. It shows as it being 1.81. Let's change the A over B of the external one. Okay, and now you can see the aspect ratio of this internal one, homothetic to the external one, which has aspect ratio of 1.91. So let's finish this video by animating this whole system so we can watch the locus of the chords, the elliptic locus of chords, for an angle of 70 degrees. In fact, let's change this angle from 70 to 60. You're going to get that when the angle between the blue rotated normals is 60 degrees. You get this. When that angle is equal to 45 degrees, you get a bigger ellipse. So what's happening is, as this, what I'm calling the Frégier angle, so the angle between the two blue arrows, right, becomes smaller and smaller, the locus of the envelope is going to become more and more like the ellipse. And why is that? Because in the limit, when we take this guy to say 5 degrees, okay, the two arrows are pretty close to each other. The chord is basically a local approximation to the ellipse, and the envelope of that chord is going to look like the ellipse itself. Okay, so here's at 5 degrees. Let's go to 10 degrees. Oops, I typed 1. I want 10. So here's 10 degrees. Let's go to 20 degrees. Let's go to 30 degrees. So you can see here that my locus is becoming a smaller ellipse that is not axis aligned. Notice that this locus ellipse has axes that are skewed with respect to the original one, which is not the case of the locus of the center, right? So we go to 40 degrees, smaller still, and we can go to 45, smaller still, and then 60. You get that picture. Now, just as I was doing this video, okay, I noticed something cool here. Look at what's happening to the 60-degree case. Notice how this ellipse is now inscribed into the triangle that consists of the two rays and the chord. So now I have the locus of my envelope can be inscribed on the ellipse if I'm at an angle. If I think I had 0 here, right? Yes. So let's animate this and try to understand this phenomenon. Yeah, so the phenomenon is the following. The elliptic locus of the envelope is inscribed in the triangle formed by the two rays that will be emitted at this particular position, right, when they are actually symmetric about the normal, by the amount 60 degrees, which is what I have right now, right? This is not the case if I have 90 degrees, this is not the case if I have 45 degrees, and this is not the case if I have 30 degrees. So there's an additional, I would say, special effect here, or special phenomenon that is related to the 60-degree blue to blue angle when I'm actually considering the triangle formed in this specific position of the blue pair, because of course this blue pair is in a way immaterial, right? You're sweeping the whole family of blue pairs rigidly, in this case with 60 degrees in between, and they're sweeping this envelope here, right? So the instantaneous envelope is right here, but this thing is going to sweep this ellipse. But looks like what we just noticed is that at the center position, so when this guy here is exactly equal to 0, right? So now what I mean is that the pair is not rotated with respect to the normal. We get a triangle which is perfectly circumscribed about the locus of the envelope of that pink chord over all rotations of the blue pair. So that's a phenomenon I was not aware of before I started this video, and it's great to do these videos because we end up discovering new things. Okay, I hope you guys enjoyed it. If you have any questions, ideas on how to prove this area invariance, if you know if this particular area invariance shown here is something that is already known, please let me know in the comments below. Thank you very much.